This last video with the series about ANSYS and using it for Fluent for flow modeling is going to show you the last steps of actually running the simulation and then plotting the results. So hopefully you'll find that after all of this video stuff, that going through this slowly like I've done means you'll be able to actually run a simulation. So let's get started. There, we click up here to run calculation. First of all, we can check the case, and it gives us some advice, but we're okay with that. And if we choose one iteration and calculate, then what you'll see is it will generate all of the plots. The scaled residual plot. Now, if I right-click on the bar here, I can embed this in the mesh plot. And if I look to the drag and lift, I can embed this in the mesh plot as well. And now what we can do is, by not changing the window, maybe we can watch the solution progress. Now the other thing we can do is we can create in this window in the graphics menu there, we can look at a contour, create a new contour. We'll have a contour of velocity, and we'll have node values. We won't have boundary values. And so you can see that this, from our first brief run, is showing us the velocity magnitudes. We can also compute some path lines. And if we select the interior surface, that would be the calculation volume. As you can see, that creates a very dense mesh. So we want to skip lots of paths and coarsen that. And this will give us a bit more of a useful plot. There. So now all we've done is one iteration, and you can see that in just one iteration, we've simulated some of that flow. But let's see what happens when we actually do, and we've done one iteration. We can do another iteration and calculate, change those settings. And you can see that, and it's recalculated, and it's given us some more path lines. And we've also increased these plots. Now the top one, you'll see, will be our residuals, and the bottom one is our drag and lift coefficients. So we've only done 2 iterations so far. So let's do 200. Now you'll see the residuals are starting to drop, which is good here. We want those to drop down to fairly small values, and it's a logarithmic scale on the vertical. And we can see that the drag coefficient and the lift coefficients are stabilizing. and the calculation is complete. Now what we've done is we've got our calculation of the lift and drag shown here, and our calculation of the residuals. Now let me see if we can move that out of the embedded window. And you can see that our residuals started off quite high, and over the iterations they dropped. And what that means is those are the residual velocities that are not adding up from cell to cell on the iterations. And they're the residual mass flows. So continuity, that would be the worst because that's not completely solved by this method. And the velocities and turbulence factors, what we want to see is these numbers dropping down to a number something like 10 to the minus 4, 10 to the minus 5. And they're going in that trend. So we could continue with more iterations. But at the moment, that's pretty reasonable. And now I can move that out of the embedded window, and we can see, so our coefficient of lift and drag started off in some crazy numbers. Now these units are not exactly making any sense, but they are stabilizing at a lift to drag ratio of something relatively high. We've got a lift coefficient of 60 and a drag coefficient of 10. That's a lift to drag coefficient of 6. So we're expecting a lift to drag coefficient of 22 or so, and so we're certainly not there yet, but then we don't really have an excellent grid yet. And as you can see in this model, in our simulation here, we're showing that there is this separation bubble in the wake. And we've seen that in the other simulations as well. And in fact, looking deeply here, you can see that there's quite a separation bubble at this point as well. And so how that behaves will be totally dependent upon what we chose for the grid and how we modeled what's going on close to the boundary layer. So I'm going to save this result, and we could carry on for more iterations, but I won't at the moment, and we'll save the project. And now that it's saved, we'll close out of Fluent. And the last thing we can do is there's a post-processing application in this, which gives a little nicer graphics. So here we are in the post-processor, and you'll see that this brings in the results as if it's a 2D, a three-dimensional slice of something. And we can just look at that plane, and we can look at the plots, and here we can insert, let's start with a streamline plot, and we'll call it a streamline plot. And for the domains, we'll use all domains. We will start from, we could choose where we're going to start from. I'm actually not going to start from the inlet. I'm going to start from the outlet, and I'm going to go backwards. And the reason I'm doing that is because I chose as the inlet the horizontal and the vertical faces, and it will just make a weird result. You can try it. And so if I start from there, I'm going to measure the velocities, and if you do that, you can see that this generates a perfectly realistic looking set of streamlines. Now we can choose a variety of things here, like color, and I'm going to use constant color. I'm going to pick something like blue. And I'm going to go back and maybe increase the number of these, make them 50, and apply. And so you can see that there's more streamlines here. Now, that's not all I want to do. I want to add another plot, and I want to introduce a contour plot. And the contour plot will be for all domains. The location, if I make it symmetry 1, that's the surface that's three-dimensionally on the back side of where this view is. You can see I can see the grid through it. If I make it symmetry 2, it will hide, one of them will hide the streamlines. I guess symmetry 1 will hide the streamlines. Symmetry 2 is what I'm going to put it on. And I'm going to use pressure, and I'm going to use 15. See how that looks. Yeah, so you can see I've got a pressure map here. Maybe I want more colors than that. And so I can make more interesting pressure models than that. I can also change the features of the legend. And I'm not going to make it scientific, I'm going to make it fixed. And precision, I'm going to make it 0. See how that looks. There's my pressure in pascals. So you can play around with plotting this. In fact, it's just like SolidWorks. It's a three-dimensional field. I've also got a contour map there. You can see of the pressures, and you can play around with the post-processing and graphics all you like. So there you have it. A rather long and painful process with ANSYS. You get the idea. It's similar to what we did in SolidWorks, but there's a lot more bells and whistles, especially with regards to editing and modifying the grid, and that's really what's essential. So I haven't gone through and tried to tweak this to get the expected result for the lift and drag, but you can see that by working some more with this, that's totally feasible here too. And what's more important is this hasn't given us the right answer either, and that's just the way it is. Thanks.